Hi everyone, and this video lesson is for grade 10 math. This is for the learning competency proves theorems on secants, tangents, and segments. So this is more on circle geometry. So we can have these two performance tasks. We can create a video proving the theorem, the product of the intercepts on 2 secants from an external point are equal, and we're gonna use GeoGebra or anything equivalent to it. Let's start. So first, we are going to create a circle. Okay, and then second, we're going to unhide the unused points. We're not gonna use the center, so we're gonna hide it. And then this point also, we are not going to use it, so we can also hide it. Alright, so next in the build guide or video guide, we're gonna create an external point, so it's a point outside the circle. Okay, so this is it. Alright, and then next 2 seconds. Okay, so pardon me with my pronunciation. So again, we're going to create 2 secants. Okay, so disclaimer, I'm not a native English speaker, so consider my pronunciation and the delivery in the language here as Cebulish. Okay, Cebuano English, Cebuano accent. So we're gonna create a secant. Alright, so this is the first secant, and then another secant here. Okay, and we can adjust. Alright, so we can adjust when needed. So let's do that. Then we're going to mark the intersecting points. So this is F and this is G. And then we are going to conjoin intersecting points in order to form a cyclic quadrilateral. A quadrilateral whose points, the 4 points, are along the circle. So this is F will be connected to G, and then D will be connected to E. And then define what are intercepts. So if we are going to have 2 secants in a circle and an external point, when we say intercept, it is a segment connecting an external point to a point of a secant of the circle. Okay, so this is a point at the circle, and this is the external point. So the line segment connecting the two is an intercept. And also, F is a point in the circle along the secant, and this is an external point. So the line segment FC is also an intercept. So again, GC is an intercept, FC is also an intercept. And then we also have E here that is along the circle and along the secant. And then we have the external point C. So connecting E and C form an intercept. So we have an intercept EC. And then G is along the circle and along the secant. And then C is an external point. So connecting G and C is also an intercept. Okay, so what is the theorem that we are going to prove? The theorem says the product of the intercepts on 2 secants from an external point are equal. So what will be the equation of the theorem? So that would be DC, okay, look at here, DC times FC will be equal to EC times GC. Now, we are going to measure all of the intercepts and then perform multiplication, okay, using the algebra tool of geometry and compare the product. Alright, to see if the theorem, alright, is correct. So let's measure. So click on distance and then click on D and C. So DC is 12 and then FC is 4.6. And then EC is 11.7 and then GC is 4.7. Okay, and then we are now going to multiply. So we have the algebra tool here, and then we're going to call the function distance. So distance GDC and then times distance FC. So that's 55.5. And on the other secant, so distance EC times distance GC is also 55.5. Alright, now so that's what's the next in the build guide, the video guide. So we're done comparing. We the algebra tool have shown that the products of the intercepts of the intercepts okay, in this 2 seconds from the external point are equal. Alright, now we are going to identify similar triangles. So can you observe that there are 2 similar triangles? The bigger triangle and the smaller triangle over here. So we have triangle DCE, right, the big triangle, and the small triangle FCG. Okay, so the 2 are similar by inspection. Now, what is the main logic of the proof? We're going to prove that the triangles are similar by proving that the 3 pairs of corresponding angles are equal. So again, we all know that the 2 triangles are similar if the corresponding angles are equal. Okay, so let's now identify the corresponding angles. So we have angle CFG, right? Look at here, CFG, alright? By inspection, okay, it will be equal with G, or it corresponds with angle DEC, alright? Okay, and it's not really CDE, okay? It's like there's we need to invert the 2 triangles. Alright, so that's by inspection. So let's measure to show equality. So CFG, that's 72 degrees, and then we have DEC, it's also 72 degrees, right? Okay, and angle FGC corresponds with angle CGE. Okay, so let's show that. So FGC corresponds with angle CGE. See, their measurements are equal, and of course, by reflexive property, angle FCG corresponds with angle DCE. Okay, it refers to the same angle. So, by reflexive property, those 2 angles FCG and DCE are equal. Alright, so we have shown now that all corresponding angles are equal. So we can say that the 2 triangles DCE and FCE are similar. Okay, now we are gonna move the points, okay, just to show to our friends and to our teacher that the equality of the corresponding angles remains the same. Okay, it's still the same wherever the points of the 2 secants will be positioned. right? Okay, now how about the product of the intercept? Okay, observe that no matter how we move, okay, the points of the secants, okay, the distance, the product of the intercepts remain the same. It's still 55.5. Okay, so we are now at the proving part. Okay, so step 1, identify the angle relationships that are supplementary. So the keyword here, you're gonna find supplementary angles. Okay, so what angle pair relationship are supplementary? Of course, we have linear pairs and we have the opposite angles in a cyclic quadrilateral. Okay, so linear pairs and opposite angles in the cyclic quadrilateral. Okay, so we're gonna show first that angles CFG and DEC are equal. So DEC, where is that? This one, DEC, and then is equal with CFG. Alright, so we're gonna make use of this linear pair here. So CFG, okay, and DFG are linear pairs. Alright, so the sum of these two angles is 180. Alright, and then we can see here that angle DFG and angle DEC are opposite angles in the cyclic quadrilateral, so they are also supplementary. Okay, so we now have this equation. Alright, the sum of linear pairs is 180, and then the sum of the opposite angles in the cyclic quadrilateral is also 180. Okay, and then so since they are both equal to 180, then we can have this equation. Okay, angle CFG plus angle DFG is equal to angle DFG plus angle DEG. The sum of linear pairs is equal to the sum of the opposite angles in a cyclic quadrilateral, because both of them are supplementary and we are being supported by the transitive property of equality. Okay, and then looking at here, we can now then do cancellation. Okay, the additive inverse. Look at here. We have angle DFG at the left side and we also have angle DFG at the right side. Both are positive, so it can be cancelled and we now have this equality of the corresponding angles. Okay, do the same, alright, to show with that logic, prove that angle CDE is equal to angle FGC. Alright. And then we have proven also that angle DCE is equal to angle FCE because of its reflexive property. Alright, and we all know that knowing that we have shown equality to all corresponding angles, then we can say that triangle DCE and triangle FCE are similar, and we can use that similarity to state the equality of ratios of corresponding sides. So what are the corresponding sides? Okay, so we have EC and FC, EC and FC, because these are the shortest sides, and we also have DC and GC, the mid-range. Okay, so we have DC and GC. Okay, and then that's why we have this ratio, EC divided by DC is equal to FC over GC. Then we can cross multiply and we are going to derive the equality of the theorem. Okay, so therefore we can conclude, alright, that the product of the intercept, okay, of 2 seconds from an external point are indeed equal. So have fun recreating this video and don't forget to reflect on the activity. Bye for now.